This is a little bit small, but let's see if we can get this to work. So, what would this thing be called? CH2D2. H4. Okay, we hear that? Okay, so I've seen a few of you put the hydrogens first. Remember, hydrogens they kind of fit between the nitrogen and the oxygen column. So even though hydrogen's over there, it's kind of an exception. Hydrogen comes after nitrogens and before oxygens.
7.5, right?
Yes, nitrogen 7.5. Okay, so watch out for that. Someone in my class, my first year, I was teaching this. They said this reminds them of chocolate, CHO chocolate. So that helps them remember that the O has to come after, the H comes before the O.
I need to put chlorine for chocolate.
Oh, there you go. There we go. Okay, good. Oh, what happens? What happens if we have sulfur and an oxygen? Which one comes first?
Sulfur.
Sulfur, why?
Because it's a
So, good. Bigger to smaller. So lower to higher in the periodic table. Okay, very good. Okay, so something like this will come up on your final. So make sure you're ready. Make sure you remember the order. Okay, let's go to our schedule. I have made a schedule for December. Let me hand you the schedule for December. So I think the most important thing this week is lab 3 on Thursday. Coming back, we'll do lab 3.
This Thursday?
This Thursday. Yeah.
Lab 2, I
We're going to have a school year. That's so weird. It's so weird. We're going to be seniors next year.
Okay, so today we're doing chapter 6. We'll do lab 3 on Thursday. So if we're doing lab 3 on Thursday, what does that mean for us?
lab 2.
Yeah, we need to do the pre-lab before you come to class. So, we can talk about that in just a second. Then labs, chapter 6 again. We'll do lab 4 next Wednesday. Again, we're just trying to catch up on the labs. Usually we catch on 4 labs before quarter 2. Then we'll have a review day. Alex, chapter 6 is due on the 11th. So make sure you're making progress on that. We'll do our chapter 6 exam. Then we'll start chapter 7. We'll do lab 5. Then we're almost caught up with our labs. And then we have our winter break. Okay. I'm not planning to do anything on this day. Year 80, right? Because that's usually just the winter assembly. All right. Questions about our schedule? Okay, let's quickly look at let me see if I can open this. Let's look quickly at the pre-lab for lab 3. Actually, I haven't looked at this yet, so look at this really quick. So this lab is separations. We're going to do some separating.
Well, let me open up the
Lab 3. Okay, so let's look at the pre-lab. Preview. Okay, so it looks like it's going to ask you some questions. Does anyone know what homogeneous means?
I have it in my own.
Homogeneous, yeah, there's all living together. So you can, okay, homogeneous or homogeneous. What's heterogeneous? not mixed very well. Random stuff throughout. Okay, with chunks. This one reminds me of like a chunky smoothie, or like soup. This would be like tomato soup, and this is like chicken noodle soup. Okay, how about we're gonna use filtration.
Cool.
So in this lab, one of the things we're gonna do is we're going to I'm gonna give you a mixture of sand and salt, and you have to separate it.
Nice.
So can you imagine how you would do that?
Yes.
How can you do that? Good. Yep. So you're gonna dissolve the salt into the water, filter off the sand. So that's what you're gonna do in this lab. You're gonna separate the sand from the water, or excuse me, sand from the salt. And then, if you have salt and water, you can use that evaporation to get rid of the water. Okay. And then, let's see, chemicals in the mobile phase. Mobile phase is, I'm trying to think of something that is not chemistry. So what you're going to do is you're going to take a filter paper, or a paper. We have some chromatography-free paper, and you're going to put a marker line. And then you're going to put it in some liquid. The liquid is the mobile phase. The mobile phase we're going to use is rubbing alcohol, okay, or isopropyl alcohol. And you're going to put a little bit of that in I think you're going to use the beaker test tube, I can't remember. And then the liquid will move up, so that's what's mobile. The mobile phase is the liquid that's moving. The stationary phase is the paper. The paper is not moving. The water will kind of like wick up the paper, but not the water. Isopropyl alcohol will wick up the paper, and then that will be able to separate the dyes. You're going to look at some markers. Okay. Let's see. So in the lab, so you're supposed to be reading this. We'll just go over it though. You're going to put the sand and the salt in water. It tells you to put it about 10 milliliters. You don't want that to boil, because if you boil it, it'll splash your sand and your salt out, and you need to make sure that you get as much of that as you can. Ideally, you would collect 100% at the end. So if it boils, it's going to splash, and you're going to lose your material. So don't boil the sand and salt mixture. Okay. Water mixture. Water, salt, sand. Let's see. So in this section, you're going to, so again, we just talked about our paper as our stationary phase. You're going to put a marker line on the bottom. You're also going to put a pencil line on the bottom, because the pencil is not going to move. The stationary phase is the paper. The mobile phase will move up through the paper. And your dyes should kind of like travel something like this. I think I have an example. Anyways, so then you're going to measure from, this is where you started, and this is where it ended. So this is your start. This is your end. So your measurement should start where you started your marker, on the pencil line. And it should end on, this is called the, so I guess you're going to measure the dye. Where did the dye get to? So maybe your dye is here, maybe your dye got to here. So whatever dye you're measuring, you're gonna end wherever the dye gets to on your paper. So marker, what's the marker color? Okay, how many are there? Oh, that's all. Okay, questions on any of those? So pretty straightforward lab. We'll talk more about it when you come on Thursday. One thing that I will try to remind you is that some of the lab you have to wait. So if you're waiting, you could do the next part. So like while you're waiting for the sand to dry, do the chromatography paper. Don't just wait for something to dry while you could be doing something else. So kind of like stagger your experiments. Okay, very good. Let's go back to, where were we? Okay, now we're going to go back to our topics. So we have 6 topics left. We'll go through some of them. And try to get through some of them. Let me see if I can pull over. I have my Alex open. It's just not over here. So I am, again, I'm recording my screen, and that webcam is helping us capture the sound, and I will post these on Canvas. Close it. Did you close up your internet? So yeah, and it sounds like you already refreshed, right? Yeah. I would try to close it and restart my computer and see if that helps. And if that doesn't help, you might have to try to go into the regular Alex. Like just go to the Alex website and like any stuff, see if that works.
When I type that in, it won't be bad, but it doesn't have.
Oh, it doesn't have fast? Yeah. Are you using your reverse date session? Your reverse date login? No. Oh, I had this right on the phone. Okay, so here, this is the next one I want to talk about. Drawing the reaction energy diagram of a catalyzed reaction. So this one should be pretty straightforward, so let's go over it. So there's a few things that we have to watch out for. So uncatalyzed is just the regular reaction. And we have to look for what it's asking us. Endothermic. So do you remember? Let's draw our two graphs up here again. Is this going to work? If I write it up here, then it screen captures it. Can you see that okay? I draw there. Okay, hopefully that is okay. So remember, we have our two types of reaction. Oops. We have endo, which is what this question is asking for. So on this type of question, make sure you're figuring out what they're asking you. Okay? Don't just pick one. Make sure you do what they ask. So endothermic, what do we look for? Going up, yeah. So our products are higher than our reactants. And then we have this activation energy that gets to our transition state. And then what about exo? The other way, yep. We start at a higher energy level, we go over the transition state, and then our products are lower in energy. Okay, so remember these are our reactants, and these are our products. And then these, the highest point is called the transition state. And I have had students flip these, so don't do that. Make sure that you get them straight. Maybe you write those examples on your note card. Okay, so this, we just have to draw a reaction. We have to make sure it's endothermic. So I'm going to put my reactant somewhere. It doesn't matter too much. I know for endothermic, my products have to be higher. And then I need a transition state. Okay? Then catalyze. A catalyzed reaction. What happens in a catalyzed reaction is, let's see, do I have another marker? No. Let me see if I can get another color of marker. So what a catalyzed reaction does is it starts in the same spot, it ends in the same spot, it just lowers that barrier. So the barrier has to be smaller. And same thing for exo, it starts in the same spot, it ends in the same spot. The barrier is just shorter for catalyzed. So pink is our catalyzed. So what this does is it just makes the reaction go easier. It's easier for the reaction to cross the energy barrier, this transition state. So the catalyst isn't part of the reaction, it doesn't get consumed, it just makes the reaction more energetically favorable. So what we're going to do is we're going to start in the same spot, and we might have to adjust, but you're going to start in the same spot, we're going to end in the same spot. So make sure on the test when you do this, they're exactly in the same spot. And then the activation energy has to be shorter. And that's all. Okay, so just make sure it's shorter. Okay. It has to have a barrier too. I don't think it won't work if you do something like that. I don't think I said it right, but that doesn't make sense. Okay. Questions on that? So hopefully that one. I'm surprised at how many people miss this question because it should be really straightforward. You're starting in the same spot, ending in the same spot. Catalyze has a lower activation energy. And then make sure that if it tells you endothermic, your products are higher than your reactants. And opposite for exothermic. Okay, questions on this one? Do you want to do another one? Or you got this one?
Let's just do one more.
Do one more? Okay. All right, so this one says, sketch a qualitative reaction energy diagram for a chemical reaction without a catalyst. Assume it's exothermic. And then do the catalyzed reaction. So exothermic, we need to make sure our products are lower in energy and our reactants are higher in energy. Again, it doesn't really matter where they are. Reactants are higher than the products in exothermic. And then the catalyzed reaction is the same reaction. Reactants start in the same spot, products end in the same spot, but our energy barrier for the catalyzed reaction has to be higher than the catalyzed reaction. So this one is easier to cross the barrier because it has a catalyst. It's more favorable. This one, it is harder to get over that barrier for an uncatalyzed reaction. Okay, questions on that? Okay, oh, I better check. And that was exothermic. Okay, all right. Now, what one are we going to do next? Okay, now we're going to start talking about equilibrium. Let me see, I have some slides on equilibrium. Pull up my equilibrium slides. Okay. So equilibrium is a little bit tricky, so let's just look at our definition of equilibrium before we talk about these next questions. So equilibrium happens when the concentration of the products and the concentration of the reactants are constant. They're just not changing. That doesn't mean that the reaction isn't happening. So things can be going to the products, things can be going to the reactants. So things can be moving back and forth, but the concentrations are not changing. So the rate of the forward reaction is equal to the rate of the reverse reaction. So these two things are key for understanding equilibrium. So these are some examples that are in real life that kind of help us hopefully get a picture of what equilibrium is. So if we have a bank account and it is at equilibrium, that means we have the same amount of money flowing in as we have flowing out. There's money that's always flowing, but if it's at equilibrium, the amount coming in equals the amount coming out. Okay? Or like a lake. If a lake is filling up with water, but the same amount is leaving, then it's overall, the level's not changing, but there is movement, right? There's stuff coming in, there's stuff coming out. It's at equilibrium if the concentrations are not changing. Does that kind of make sense? Okay. So a lot of times students think that equilibrium is if the reaction is stopped. That's not true. The reaction can still be happening, just the rate of the forward reaction equals the rate of the reverse reaction. Okay. So what we're talking about when we are talking about forward and reverse reactions are something like this. So if we have, like in our energy diagram, it said, oh, we have A plus B goes to C plus D. That's our forward reaction. This reverse reaction is also happening in a reversible reaction. So this doesn't happen in all reactions, like combustion. Usually things don't uncombust, okay? But if we're doing a lot of things in solution, are reversible. They can go forward and they can go backwards. And that's a little bit confusing to think about. So our products can be forming our reactants and our reactants can be forming our products. So we use this little arrow to tell us if it's a reversible reaction.
They're going back and forth, even if it might be going one direction more.
Yes, perfect. Yep, good. Yes, and often it is favoring one direction. One is favored. But yeah, that shows us this is a reversible reaction. It can go forward and it can go backwards. Okay. Oh, let's see. Did I miss that? Let's see. What does this say? Okay. So to be able to do this, you have to have products and reactants. If you don't have any products, then you can't go backwards because you don't have any products to make your reactants. Okay, so that's something that comes up in the Alex questions. You have to have products to have your forward and reverse reaction. Okay, I think that's good. Let's see. Okay, so then we have to understand this concept. This is tied to a principle called Le Chatelier's principle. So if we have this reaction and it's at equilibrium, the reaction is going to try to always be at equilibrium. So if you mess up the equilibrium, it tries to go back to equilibrium. So if we have this reaction, A plus B goes to C plus D, and we add, and it's at equilibrium, it's all balanced, the forward rate equals the reverse rate, and all of a sudden we add more A. The reaction is going to move away from what we add. So it's, oh, we have more A, we can make more of C and D. So it's gonna, the forward rate will increase until it can reach equilibrium. Okay, so it moves away from anything that you add. Okay, so if we added, I think I have another example. What is this table telling us? Let's go back. If we add more C, if this is at equilibrium and we add more C, what's going to happen to our reaction?
The reverse reaction.
Yeah, reverse reaction will increase. Yeah, it was at equilibrium. We mess up the equilibrium by adding more product. The product will start forming more reactant until it gets back to equilibrium. Okay. All right. So this, I think this table is from Alex. So let's see what Alex is telling us. If our forward rate is greater than the reverse rate, then that means we're getting more products. If our forward rate is less than our reverse rate, so if our forward rate is less than the reverse rate, that means we're getting more reactants and less products. If they're equal, if these rates are equal, then that's when it's at equilibrium. If the forward rate is equal to the reverse rate, then that's our definition of equilibrium. Our reactants and our products have a constant concentration. Okay. Question so far, does that sort of make sense? Oh, does anyone know what time we get out for this class? I feel like this is 5 minutes. 5 minutes ago. So 12, 25, 35.
Yeah.
Perfect, thank you.
Also do 10 minutes later.
You what?
I think it's just 10 minutes later. It's
Oh. You're gonna leave 10 minutes later?
No.
Oh.
Because I was thinking, well, the last class was 5 minutes later. So this class would be 10 minutes later, but that doesn't make sense. It would just be 5 minutes later.
Okay.
I'm making this complicated.
Okay. All right. Oh, okay. And we talked a little bit about this. So this is Le Chatelier's principle. If a chemical system at equilibrium is disturbed or stressed, the system will react in a direction that counteracts the disturbance or relieves the stress. So some of the things that we can change are concentration, temperature, and pressure. And these all come up in the Alex topics. So if we change the concentration, the reaction is going to try to get back to equilibrium by changing some of the concentrations, changing the rates. We can also change the temperature, and we can also change the pressure. And we'll go over these examples in an Alex question.
Oh.
Okay. All right, so here is an example with concentration. We'll do this, we'll just do that now. Let's go back to our Alex and see if we can do some of the questions now. Okay, what one was next on the list? We did not predict relative or, okay, good. Predicting relative, or is it? You see it? Oh, is it? Is this the right one? This one doesn't seem right.
No, it's.
Oh, there it is. Okay, I maybe pass it. Okay, and so for equilibrium to happen, we have to have both the reactants and the products. And I think that's something that tricks students a lot on this question. So I don't know what this is. Oh, it is blocking my picture.
There's no picture.
Or not my picture, it's blocking this word. Okay, nitrogen and hydrogen react to form ammonia, like this. Imagine 208 millimoles of ammonia are added to an empty flask, and then answer the following questions. So first, you have to picture what you have before the reaction starts. Some of them have an empty flask. If it's empty, then you have no reaction. Okay. The only time it can be zero is if there's nothing in the vial. Okay. All right. So it says, what is the rate of the reverse reaction before any ammonia has been added? Well, we started with an empty flask. Before we add ammonia, what's happening? Nothing happening. So 0 is our rate. Okay, 0 reaction. Does that make sense? No?
It's greater than 0 but equal to the rate of the reaction. Because we also still have hydrogen inside with the
Oh, sometimes, yes. If there's something in the vial, yes.
I didn't see that.
You just have to be careful about if it's empty. All right, so the next one. What is the rate of the reverse reaction just after we add ammonia? So it's empty, we add ammonia, and we look at the rate. So if we add ammonia, so remember this is reversible. We can have something going forward and something going back. Which rate is going to be greater, faster? More things happening. The reverse rate from ammonia to the reactants or the reactants to the product? The reverse is going to be greater. Good. Greater than 0. Let's see. Greater than 0, and greater than the rate of the forward reaction. Okay, because we don't have any reactants right now. It's empty. Then we add ammonia. We don't have any of the reactants to go to the products. Okay. Okay, then it says, what is the rate of the reverse reaction at equilibrium? So we waited for a long time. Now the reaction is steady. It's called steady state. It's at equilibrium. What is the definition of equilibrium? Well, our definition of equilibrium is that our rates are greater than 0 and equal to the rate of the forward reaction. So anytime it's at equilibrium, you should pick they're greater than 0 and they're equal. When the rates are equal, that's our definition of equilibrium. Does that make sense? Okay. All right, last question. How much ammonia is in the flask at the equilibrium? So we started with 208. This is the only thing we added, but we are having this reverse reaction and the forward reaction. So how much so we can go forward and back. How much do you think we'll have at the end?
Probably more.
Some, but less.
Right, because so we're gonna have some but less because we won't we'll have used some of that up to go to the products. We can't get more because that's as much as we added, and we like put it in and we seal it. It's a guess, so you can't get more than that. we do have that reverse reaction happening, so some of this got used up to make our products. We don't have none because it's reversible. Okay, let's check. This one is tricky. Okay, questions on that? Okay, let's do another one. These ones are a little bit tricky. All right, so methane and water react to form carbon monoxide and hydrogen like this. Imagine you have 246 millimoles of methane, 246 millimoles of water are added to an empty flask. So now that's a key. Make sure you're paying attention. Is it empty or does it have stuff in it already? Excuse me. This one's empty. We started with the empty. What is the rate of the forward reaction before any methane or water has been added? So you're looking at it empty flask. What's the rate? 0. Nothing's happening because there's nothing in there. Okay, what is the rate of the forward reaction just after you add methane and water? So make sure you're paying attention to what side they're on. Methane and water are the reactants. So right after you add those, the forward rate is going to be greater. So the rate greater than 0 and greater than the rate of the reverse reaction. Because there's more reactants to make the products. Next question, what is the rate of the forward reaction at equilibrium? What's the definition of equilibrium? They're going to be equal. At equilibrium, the rates are equal. Greater than 0 and equal to the rate of the reverse reaction. So if you miss all of this question, make sure you get this one. The definition of equilibrium is that the rates are equal. Okay. How much methane is in the flask at equilibrium? So remember, we didn't have anything to start with. We put in 246. Some of that went to our products. So we're going to have some, but we're going to have less than what we started with. Okay. So hopefully you're starting to see a pattern on these. Okay, let's try one, see if we can find one that it's not empty to start with. Good, okay. All right, so this one's different. Acetic acid and ethanol react to form ethyl acetate and water, like this. Imagine 240 millimoles of, what's this one? Ethyl acetate, so this is a product. Okay, so make sure you're paying attention. This one's a product. Is removed from a flask containing a mixture. So it has a mixture of all of our reactants and our products. This is not an empty flask, okay? And it's at equilibrium, so there's some keywords. We have a mixture at equilibrium. So what is the rate before any of the ethyl acetate has been removed? It's not empty. It can be 0 if it's not empty. And it's at equilibrium. So before you do anything, you come across this flask, you've been watching it for a while, it's at equilibrium. So at equilibrium, make sure you pick this one. It's greater than 0 and equal to the rate of the forward reverse reaction. Okay. Next one. What is the rate of the reverse reaction just after we remove ethyl acetate? So let's go back here. So we pull some of this out. It was at equilibrium. We pulled some of this out. What's going to happen to the reaction? You wanted it to be at equilibrium. It was at equilibrium. You removed some of this. So the reaction is going to try to balance that. If you pull something out, the reaction will try to fill that hole. Okay? So you pulled this out. It's going to try to replace what you pulled out. So initially, the forward rate is going to be greater. Does that make sense? Because it's trying to fill up what you pulled out. So let's see what we're trying to find one that says the forward rate is greater. What is the rate just after ethyl acetate is removed? So it should be greater than 0. So not 0, but it should be less than the rate of the forward reaction because the reaction is trying to move forward to replace what you pulled out. Okay, hopefully I said that enough times. What is the rate of the reverse reaction when the system, again, has reached equilibrium? So keyword here, equilibrium. What are we going to put? Equal. Equal, because they're greater than 0, but equal to the rate of the forward reaction. Good. All right, how much less ethyl acetate is in the flask when the system has again reached equilibrium. So you pulled out this much.
So none.
Let's see. So we started with some. We pulled out this much. Our reaction balanced. Let's see.
Just none less.
Yes, there should be some missing, but less than 240 missing because our reaction balanced to 240. Okay. All right. Check. Okay. All right. Questions on that one. So hopefully you're starting to see some patterns on this question. I think we've gone through. There's only 2 types. I think. Or there's a few variations, but one that's empty and one that's not empty. Did you have a question?
So if you pull it out of the product side, the reverse is the faster,
If you pull it out of the product side, the forward is going to be faster.
forward is faster.
Because you're trying to replace the products.
Okay.
So the reactants are going to, oh, we need to make more. There's like
And then
a
if you
double
pull
weight.
out of the reactants, the reverse will be faster.
Yes, that's true. Good. Good. Okay. All right, let's go to our next topic. Okay, so now we're getting to equilibrium. Let's go back to our slides. Do we miss one? Writing concentration. No, I don't think so. We did that already. Okay, let's talk briefly about concentration, and then we'll talk about the equilibrium expression, and then we'll do one more, at least one more Alex topic. Okay, so concentration in chemistry is how many moles of something there is divided by the volume in liters. So this is like a definition of concentration. We have lots of different units for concentration, but these are the ones that we use the most, okay? And if it's moles per liter, so how many moles in a liter, then we use this big M called molarity, okay? Don't use capital M for moles, that gets confusing. Use MOL for moles, use capital M for molarity, moles per liter. This is a concentration. So it's like, how much sugar do I have in my bottle? Moles per liter. And so this is another place where moles comes up. We might need to use the molar mass to convert grams to moles. Okay, all right, so that's concentration. Concentration comes up in this reaction, or this equation. So we have, this is our chemical equation. The little a, the little b, the little c, the little d, those are supposed to represent the numbers in front of the chemical. So this is like, I have 2 moles of A plus 4 moles of B, okay? Those are our coefficients. And then we have our equilibrium constant. This is something that you will need to calculate. To calculate the equilibrium constant, we use this little bracket thing is telling me that's concentration. So the concentration of C to the power that's in front of it. So if this is a 2, then it's going to be a 2. And notice this is the products over the reactants. So I think this is what I remember the most. Oops. Products over reactants. And then I can just remember, oh, it's the concentration of the products raised to each of their coefficients divided by the concentration of the reactants raised to their coefficients. And we just have multiplication in here. That didn't make a lot of sense. Does that make sense? Are you following okay? I think if we do an example, it'll make sense. Okay, so if we do this one down here, the equilibrium constant expression, can I draw in here? How do I do that? This is PowerPoint, so I can't. Drawing tool. Pen. Let's see if I can use my pen. All right, so we're gonna do our product. So we're gonna look at I didn't do my. Where's the? Now it turned it off. And my pen tool change. Okay. Okay. So we are gonna do our equilibrium constant is going to be the concentration of our products. So these are our products. That's a squiggle. Times by the concentration of our other product. This one doesn't have any coefficients, so all of the exponents would be 1. Okay. If this had a 3 for some reason, it doesn't. But if it had a 3, then I would put the 3 here. Okay. So let's erase that. See if we can get the. Okay. So it doesn't have a 3, so we don't put 3. Does that make sense? So that's where our coefficients are going. If we had coefficients here. So products raised to their coefficients divided by our reactants concentrations raised to their coefficients. Okay. All right. Questions on that? Okay.
Why is it that the one with hydrogen goes before the other? Like in the when you're writing the
Oh, here?
Yeah.
This?
well for products.
Oh, I just picked that one. It was closer with my eyes. I just saw that one first. Yeah, because multiplication, you can flip it. It doesn't matter for multiplication. Yeah. Yeah, you can put this one first on the top. I just saw this one first, so I wrote it first. Yeah. Good question. Yeah. Thank you for asking that. Okay. Are we good? Yes.
Sorry.
No, you're good.
This we just
Yeah.
write out the expression. We don't like solve it or anything.
Not for the. There's 2 types of questions actually.
Okay.
And for one of them, you just write it out.
Okay.
Yeah. And one of them, you do have to solve something, I think. So let's do both of those. We'll see. Maybe we'll do one. And we'll see on our time. Okay. There's another question that asks about pressure. So if they're all gases, so we're looking at them, the phase is all gas, then we're going to do the same thing, but instead of concentration, it's going to give us pressure. So the pressure of the C times the pressure of D, all over the pressure of A times pressure of B, and then raised to their exponent. So let's do this one, or you try this one. See if you can write the equilibrium constant expression, and then I'll write it up here. So what would we write for our equilibrium constant expression for this methane plus chlorine gas gives us methylene chloride and hydrochloric acid. All as gases. So we would need to know the pressures of all the gases. Okay, I'm gonna write it up here. So our pressure equilibrium constant, does it make me put, I remember I have to use the back of my pen. I need to figure out that. So my equilibrium pressure expression would be, so products over reactants, so these are my products. I'll put this one first this time. So I just put CH3.
Oh no.
Okay, that's a 3. To the 1 times this HCl to the exponent 3 all over my reactants, which are methane, CH4, times by this other one, chlorine gas, raised to also the 3. Okay. See how that works, where the exponents come from? Okay. Okay. Very good. I think, yeah. Let's go to that. We'll do something like that now. We did that one. Writing a concentration equilibrium constant. Writing. Okay, so this is just like that. So look at the number in the front to raise it to the exponent. And remember, it's products over reactants. And this one is not all gases. So I'm going to type this in my brackets. So this is just, oops, I did that. Did it come up to the square bracket? Yeah. Okay, so the concentration of H plus, first plus, bracket, times by the concentration, oops, square bracket, of the other reactant, which is S. Oh wait, we need an exponent here. This has a 2 in the front, so we need to put this to the exponent. To the 2, oh, not 23, 2, times, bracket, SO4, bracket, to the, oh, I forgot. No, we don't have a to the. Here is the to the. So this is sulfate ion, anion. And there's only a 1 there, so we don't need to put the exponent there. Okay, and then, so remember products over reactants. Our reactant is H2SO4. So I need, for my equilibrium expression, I need the concentration of the sulfuric acid. H2SO4. And then my bracket. Okay. Okay. Questions on that? Do you see where things are coming from? The exponents. Okay, let me try another one. Let's see if we can get pressure. Oh, these ones are the same. So same things. I need concentration of the product, which is phosphoric acid, H3PO4. Oops, that's the wrong button. H3. How do I get rid of that phosphorus? H3PO subscript 4 bracket. So that's my products over my reactants. So I have H plus, and that has a 3 coefficient. So this needs to have raised to the 3. Oops, is that 3? Times by the concentration of this phosphate ion. Oh, that's nice. PO4 3 minus. That's the ion. So we need that. We need to measure the concentration of this ion if we want to calculate the equilibrium expression. So products over reactants, any coefficients need to become exponents. Okay. So pretty straightforward. I think when people miss this question, they either don't know what's going on or they put like the wrong number, or they like make something up and put it in the box. So just copy these, write the same down in the Alex. Okay. Questions on that? Okay, better check it. All right, where are we? Writing. Okay, we have 3 left. We have 1 more day. Do you want to keep going? Do you want to do these 3 next time? Work time? Next time. Okay, yep. So we'll do these last 3 next time. They are all on equilibrium, so you might be able to do them during work time. You can probably figure them out. Okay.